Hello everyone, my name is Ashley Russell and this is my 350 final project. So to start off, this is a problem description. So the problem tells us that Amazon has up to 30 lockers that they wish to install to provide service for 300 customers. Each locker costs $50,000 and customers do not want to travel more than 30 kilometers to a locker. Additionally, each kilometer a customer travels costs Amazon $100. So the objective is to minimize the total cost of the locker installations and minimize the cost of customer travel distance. So on this slide is kind of the plan that I had for this project, the schedule. So it starts off with we had to give Dr. Hom a proposal, and then we have our MIP formulation, pseudocode, the progress report, and then for this section of the project, the OPL code, the CSharp code, and then also the video. So here is my MIP formulation. This took quite a bit of thinking to work through all of this, but basically the I is the customer and J represents the locker. So in this first line, the A of IJ is the assignment of the customer to a locker. The D of IJ is the distance between a customer and a locker, and then the X of I is the locker assignment, so if a locker is used or not. So the objective function is to minimize the sum of 100 times the assignment of a customer to a locker times the distance of that customer to a locker plus the sum of 50,000 times the total number of lockers that are assigned. And then there are 4 constraints that this is subject to. So this first one basically is saying that every customer has to be assigned to only one locker. The second one is that's the constraint for the distance. So each customer can only travel 30 or less kilometers. So that's what the second one is for. And then this third one is basically saying that every locker location can only have one locker. So one location can't have 2 lockers there. It has to have only one or none if it's not used. And then the last constraint is that all of these values are binary. Okay, so here is the OPL model. It was actually fairly simple. So you start off with declare your variables and you bring in the data. So you have your customer data and your locker data, excuse me. And then you bring in your distance matrix, which I'll show you later. And then this next part is tells you like for which lockers are being used. So this is, if you go back to the previous slide, this is the X of I here for the used bracket locker, and this the 0 to 1 makes this decision variable, and the next one binary. Then we have here's the objective function, which we already talked about, was to minimize the total cost of everything, so the cost of the locker assignments and the cost of travel distance by customers. Then below are the constraints. So I just talked about that on the last slide, but this is just the Cplex code for it. So the first one is each customer must be assigned to only one locker, and then the second one is each location can have only one locker, and then the third one is the distance between a customer and a locker must be less than or equal to 30. And then this is based off of what Dr. Hom gave us for how we want the answers to be displayed. And then here is the data for the model. This is only a portion of it because the distance matrix was huge, so this is just a snippet. But so at the top we have our locker data, and that goes from 1 to 30, and then below that is the customer data, which goes from 1 to 300, and then obviously the distance matrix for the locker and customer, and that was really big, so I just took a small picture to give you an idea of what that would look like. So here on this slide are the results of my OPL model. So in the pink is the I guess they answer the number of lockers that are actually used. So lockers 2, 5, 11, 16, 19, 20, 22, and 28 are used. And then in the blue, this again is just a small picture of what the whole answer, the whole thing just wouldn't fit on here. But this tells us which customers are assigned to which lockers. So if you look in the first line, customers 11, 22, 31, and so on are assigned to locker 2. And then if you go down to locker 5, you have customers 8, 9, 29. And it just continues like that for all of the customers. So the second portion of the project was to be done in C#. So here is some just general pseudocode for the C#. So you have to load in the data for the locker coordinates and the customer coordinates. You had to set up constraints for costs and customer travel distance, and then use a loop to assign all 30 lockers in an optimal location, calculate the total cost, and then go through again but assign only 29 lockers. So repeat this by taking away a locker until customer constraints can't be met. Then you select the best iteration and create a visualization for the location of each customer and locker, then output the assignments of each locker. And then once the lockers are assigned, you need to calculate the cost of the locker assignments and the customer travel. So you start off with 30 lockers, so you use all of the available lockers and then find the cost. Next, you use 29 lockers, so you use one less and then find the cost and compare. So you do this until you find a minimum cost value or the distance constraint can be met. So as far as actual C# code goes, unfortunately I could not figure it out. I could get the pseudocode and I could logically understand what you needed to do, but I couldn't actually get the code to work. I'm not a programmer. Programming doesn't come easy. So I unfortunately had to take the L on the C#. But as far as conclusion and lessons learned goes, this is a very challenging project, and using IBM Cplex is a really good way to solve this type of problem. The language is just built for this type of problem, and it was a lot harder to solve this with C# because the language wasn't made for that type of problem the way Cplex is. But either way, I learned a lot more about Cplex and how to use it to solve optimization problems.